So we're going to talk about the modeling, right? So we're going to talk about this, especially, using mixtures, and then how we can work with systems in modeling this problem, and then how do we solve using the way that we solve solving systems of linear equations, right? So let's take a look at this. Can someone read this for me? The problem. All right. So so we have a setting, as you see in the picture right here. As you see the picture right here. So that's a setting right there. So the way that it is set up is that, so here's a tank A and here's a tank B, right? We have two tanks, and the tank A contains 50 gallons of water, right? So this has a 50 gallons of water, out of which, right, 25 pounds of salt is dissolved. So this has 25 pounds of salt in this one, right? And the tank B contains pure water, 50 gallons of pure water. So at any given time, each tank contains 50 gallons of water, and some of them is going to have salt, some of them is not going to have salt, so or you're going to have different concentrations of salt. So initially, this one has the tank A has about 50 gallons of, sorry, 25 pounds of salt, and this one has no salt, right? So keep that in mind. Now, what is happening is that the liquid, right, it's pumped into and out of tanks, as you see in the picture. So the water is coming in, it's a pure water is coming in, and the water from this mixture. So this has been well stirred, right? And this has been getting into this, and this also being well stirred. There's like a stirrer there, if you want to assume that there's a stirrer there. So that also gets stirred, and 3 gallons of water, right? 3 gallons of this mixture is being going out, and also 1 gallon per minute, right, is also coming inside this. As you see, the amount of in should be amount of out, right? So if you take a look at this one, there is a 50 gallon in here, 3 gallon per minute is coming in, and 4 gallon per minute is going out, and 1 gallon per minute is coming in. So which means from here, 3 gallon is coming in, and technically 4 gallon is coming in and 4 gallon is going out tank A. So which means that keeps the amount of water, the amount of mixture, the amount of the liquid in this one is at any given time 50 gallons. So therefore it doesn't get empty. So if you look at the tank B in here, what is happening is 3 gallons per minute of this current mixture, whatever that is going out. And if you take a look, 4 gallon is coming in and 1 gallon is going out. So that's a 4 minus 1 is 3 gallons. So the amount of mixture, the amount of liquid in this tank B is also same at any given point of time, right? So we need to keep that in mind. So now we are going to model this, right? So what is changing in these tanks is the amount of salt. So this one has 25 pounds of salt initially, and this one has no salt. Now what is happening is we are adding pure water, right? We are adding a pure water. That means it's going to dilute this, dilute the amount of dilute the water, the mixture. So the amount of salt in the tank A is going to go lower and lower, because it's also sending it back over here. Now this one has no salt at all, but the mixture from the tank A that already has a salt is coming into this. So therefore in the tank B, the amount of salt is going to go up, right? Amount of salt is going to go up. The tank A, the amount of salt is going to go down. So what we are going to do is we are going to now model the amount of salt in each tanks at any given point of time, right? So how do we do that? For that, let's take a look at a couple of things. I'm going to say, number one is, let's give some names. Let's say x1 of t. The x1 of t is the amount of salt amount of salt at time t, right? At time t is the x1 of t. Let's say x2 of t, that is the amount of salt at t in tank B, right? So I'm going to say in tank B, and I should say here in tank A, the tank A and the tank B, right? Now, what can you say about x1 of 0, ladies and gentlemen? Can someone tell me what would be the x1 of 0? The amount of salt at time t equal to 0, the initial amount of salt in time, the tank A. Can anyone say what would that be? 25 pounds, right? Very good. So I'm going to say that is 25. What is the x2 of 0, ladies and gentlemen? Can someone say that? Remember, this is going to be on YouTube. Keep that in mind. What is x2 of 0? And 0. Very good. Thank you. All right. So we have x1 of 0 is 25. x2 of 0 is equal to 0. So we have this now, right? Now let's take a look at how things are changing. The amount of salt is changing in the tank A and the tank B, right? So if you take a look at the tank A, what is happening? The rate of change, x1 prime of t, the rate of change of the salt in the tank A. So what is happening? It is receiving 3 gallons per minute of pure water, right? It is receiving 3 gallons of water per minute with pure water. That means there is no salt has been added, right? So there is no salt has been added to the tank A from the amount of liquid that it is receiving, but it is losing out at every given time, at any given time, it is losing out whatever the current concentration is, right? It is losing out 4 gallons per minute, right? It is losing out 4 gallons per minute. So let's just say the amount of salt, right? Or in this case, the density, the concentration, right? The concentration is going to be, let's take a look, is going to be this one. So if you take a look at this, it is receiving 3 gallons per minute, and there are no salt at all. So in other words, this does not provide any salt to my A. It does not increase any salt to my tank A, right? So the per pound per gallon is 0, right? Now it is also receiving 1 gallon per minute from tank B, right? So then whatever is the amount of salt, salt, right? The x2 divided by 50. I think this, rather than saying amount of salt, I think here is more of a salt per gallon, right? So it's going to be a salt per gallon, right? Amount of salt per gallon, concentration of that, right? So that is going to be x2 over 50, because whatever is the concentration in here, right? Whatever is it's a 50 gallon. I have 50 gallon, and let's just say this has a 25 pounds. That means that per gallon has half a pound, right? If this tank B has 50 pounds of salt and it has a 50 gallon, that means that every pound is going to have 1 pound of salt, right? So that whatever that we don't know, because that's keep on changing because of the way that we have. So it's going to be x2, the amount of salt, right? The amount of salt divided by the amount of gallon, which is 50. That is the amount of pound is per gallon, and that is being added 1 gallon per minute to the tank A. And by the same token, it is also losing out. 4 gallons per minute of how much of salt? Whatever is the x1, the amount of salt divided by 50 gallon, because that's a total amount, that's a capacity, right? Pounds per gallon. So here is my input rate, and here is my output rate. So let me simplify this. So that's how we are modeling this, right? You see how we are modeling, right? Now, if I simplify this, so this is going to give me the amount of salt, right? You see here, so it's going to be, the gallon is going to get canceled. So you're going to have 3 times 0 pound, which is 0, right? So this is going to be 0. It's coming in, amount of salt coming in. Because of this is going to be 0 pounds, right? And because of this, how much is coming in? 1 gallon, and the gallon gets cancelled. So I am going to have x2 over 50. Whatever is the concentration, whatever is the amount of salt divided by 50 is coming in because of this intake. Right now, what is the outgoing, right? So now it's losing 4 gallons per minute, right? Times whatever is the initial, whatever that it's currently has. So therefore, gallon gets cancelled. So we are going to have, for every minute, it is going to lose x1 over 50. So I have a 0 plus 1 times x2 over 50 minus 1 times x1 over 50. If I simplify all that, ladies and gentlemen, I would like to write this in the usual way. And if you no, I think I made a mistake. This should be 4 times x1, right? This should be 4 times x1 because it's 4 gallon. I'm sorry, right? So therefore, if I simplify all that, I am going to have this particular equation right there, which is x1 prime of t equals minus 2 over 25 x1 plus 1 over 50 x2. And similarly, if I repeat the same process for the x2, right? The same process for the x2, and as you see here, x2 as it relates to the tank B, it is losing here and here, and it is gaining through here, right? So let me use a different color. So it's losing here and gaining through this. And how much is it losing? Whatever is the current concentration, which is x2 over 50, right? Times 3 gallons per minute, right? It's losing 3x2 over 50. And it is gaining, and also it's losing here also, by the way. It's losing here also, whatever the current concentration divided by 50, 1 gallon, and it is gaining because of this, right? This is negative because it's losing. Because of this, it is gaining 4 gallon times per minute times whatever is the concentration of the x1 divided by, not multiplied by 50, divided by 50. So that's what is happening with the tank B. And so therefore, if I plug that back in here, it's gaining this, and it is losing this much and this much. And if I simplify all that, this is going to be 4 times x1 over 50, 1 times x2 over 50, and 3 times x2 over 50. So as far as x1 is concerned, it's going to be 2 over 25 x1. As far as the, so that's what we have. As far as the x2 is concerned, we are going to have 3 minus 1. 3 plus 1 is 4 because both are negative. So it's going to be 4 over 50, which is negative 2 over 25. So that's how we model this, what we call the tank problem or two tanks problem or mixer problem. And when we do that, then the differential equation that we get, is the following, and that is x1 prime of t equals minus 2 over 25 x1 of t plus 1 over 50 x2 of t, and x2 prime of t equals 2 over 25, it's positive, x1 of t plus, minus 2 over 50 x2 of t. And that's the system that I have, system of differential equation. And then we can add this initial condition to this. Now you have a differential equation, actually initial value problem. And we know that this initial value problem is going to have a unique solution. So without actually doing anything, physically, without doing testing every single time or every single minute or every single hour, we can actually figure out at any given time, if this runs smoothly, we can figure out the amount of salt, in this particular one. The salt is not a big deal, but if you are dealing with the chemicals, right? If you're dealing with the chemicals, you really don't want people to go, and check, how much chemical does it have, especially if the chemicals are harmful, right? But if you have a differential equation, set it up, this differential equation can tell you at any given time, right? The amount of salt, what is going to happen, the amount of chemical in the one tank and the amount of chemical in the other tank, and so on. So this differential equation, you can actually find the actual value, find the actual amount of chemical, even if it is harmful, and so on. Without even touching it, we can actually figure out the amount of chemical by just solving this differential equation. And again, you're all experts, so I'm going to let you solve this equation on your own. So go home and solve it. If you solve this, the solutions are going to give you. I'll probably will do the problem. I'll give you the solutions maybe later today. If you solve it, you can actually find the solution to this. Actually, as a matter of fact, the solution is, here's a solution to this one. Here's a solution to that problem. So here's the problem, right? We know how to solve this problem, right? We looked at it earlier. So if you try to solve it using the operator method, or operator, or the elimination by the process of elimination method, you can actually solve this differential equation, and then you get the solution to be this and that. So the solution is x1 of t is equal to 25 over 2 e to the negative 2 over 25 plus 25 over 2 e to the negative 3t over 25, and the next 2 is 25 e to the negative 2t over 25 minus 25 e to the negative 3t over 25. Even if you graph them, you see that the graph looks like this. It's very interesting. If you look at the x1, because of we are adding water, it's always going to get diluted, and then eventually it's going to go to 0, right? Because eventually, if you do this for long enough, you'll keep on diluting, eventually it'll have no salt content. But if you take a look at the x2, the tank 2, what is happening? Since initially it does not have anything, right? What's going to happen is that it's spiking up, the amount of salt is spiking up, and then it is going to reach the maximum. That maximum seems to be 10 pounds, right? So 10 pounds. Once it reaches the 10 pounds, then it is kind of slowly going down, because we are keep on adding, diluting the tank A, and the tank B gets the salt from the tank A, right? So therefore, it's also going down, and eventually also becomes a pure water, right? When t goes to infinity, then both of them becomes a pure. They're going to have some salt at any given point of time. There's going to be some salt, but when t goes to infinity, the both of them will eventually become 0. And actually, you can see that we can also figure out what is the maximum amount of salt that the tank B is going to contain, and so on. And we can use this model, especially if you're dealing with chemicals. If you're doing, some people are dealing with some sort of a hazardous chemical, without actually having to solve this or run this experiment, we can see what it is. And you see here, this kind of tells you that the maximum amount of the salt in the tank B is 10. So if you're designing some sort of a tank for a chemical, now you know what amount, the highest level of chemical is going to be in the tank. And so therefore, you can make appropriate precautions or appropriate measures. You can do that during the construction of that the tank, so the tank will not be harmful, right? Or the tank can withstand this the whatever the harm that can come out of this the 10 pounds of that particular chemical, or whatever that would be. So without actually having to run it using mathematics, we can figure out what is the maximum, what is the minimum, and things like that. So here's the one here's the one problem, a mathematical problem where we can solve using differential equations, and precisely exactly we can solve them without actually having to do anything there. All right, so let's take a look at some other applications, right, of our linear models. One of the things that I'm sure you have seen this in your college algebra, growth and decay. I think I kind of mentioned it earlier. The growth of any population. This is a very simple model. Let's just say if it keeps on growing, the rate of change, right, is some sort of a growth rate times the amount of population, and here is the initial population. Then it's always gonna it's always gonna grow. We know the solution to this. The solution to this would be x of t equals e to the kt, and times, I should say, times is going to be x naught, that initial population, times e to the kt. We know how to solve them. And here are some problems where, if you have a bacteria culture, and let's just say the bacteria is growing, bacteria, let's just say it's keep on growing, and then you can kind of model that. If you model that, you can actually predict the growth of the bacteria, assuming that it's kind of it grows forever. And we could also use the aging problem that half-life of plutonium, or carbon dating. People use it to find the age of any fossil, or age of the old documents and things like that. We can use a carbon dating that comes into a decaying problem. They'll see how much of carbon 14 is left, and I think carbon dating basically means the amount of carbon left. The half of the amount of carbon is, like, I think 5715, I believe. 5715. It takes 5,730 or something like that, right? 5,730 years, right? For the half life of carbon 14. Using that, you can model the decay. So the amount of carbon left in any organism, or any artifacts, you can figure out the total life of any artifact by doing the decay equation. And that, again, equation also comes from the fact that dx over dt equals kt, where here the k is negative number, that's a decaying. And then if you know the initial value, you can do all that. And there are some problems. Again, you have done these problems similarly in your similar problems in your college algebra, so I'm going to skip that for that reason. And then here's another problem of Newton laws of cooling and warming. Probably we'll talk about this more. And then we just talked about mixture of two salt solutions, and how do we work with that in systems, and so on. But what I want to do now, we'll talk about the series also later, but what I want to do now is I want to take you to one nice problem, probably that is pertinent to what we have been doing, and that is basically a population dynamics problem. So these are nonlinear models, and how do we solve some of these problems? And especially this is important, for example, for a problem like this. Let me give you a problem. So since we are dealing with the coronavirus, right? So it might be very, very interesting to some of you. So can someone read this problem for me? Can someone read this problem for me? Not Fernando, somebody else. So actually, this is the problem that we're dealing with now, right? There are people carrying coronavirus these days, right? And they are all over the place. And our campus has about 16,000 students, right? So there is a rate at which the virus is spreading, and that is actually proportional to the two things. Number one, it is proportional to the number of infected students, and also it's also proportional to the number of students who are not infected. For example, if everyone is infected, right, it's not going to spread anymore. That's it. It reached the maximum capacity, and that's it. Nobody's going to get infected, right? There's only one person is infected, and there's 1,000 people. The rate at which it's going to infect is going to be smaller compared to there's a 10 people, and infected, and there are thousands uninfected students, right? So how do we model this? So there's a one type of modeling is what we call the logistic growth, right? There are also Ali effect and so on. We'll talk about in a moment. Ali effect is more realistic than the logistic growth. Uh, so how does it work? So this logistic growth assumes the following. So um, the logistic growth is basically, here's your carrying capacity, right? The growth is the what we call per capita growth rate, right? What we call per capita growth rate is basically starts at this particular value, and the per capita growth rate is always going down to the k. So basically, when it reaches the k, the total amount of people, if you have 1,000 students on a campus, this k would be 1,000. After it's reaching 1,000 students, right? There are no more students to spread anymore. So therefore, the per capita growth rate at 10,000 is going to be 0. For example, in the case of US, in the coronavirus, we have about 300 million population. Hopefully not, suppose if it infects every one of them, after 3 million, there's no people to infect, right? So it's going to stop right there. So in the case of coronavirus in US, the carrying capacity would be the total amount of population, which is about 300 million. It's a little bit more than that. For the sake of simplicity, let's just say it's a 300 million, right? So here is the initial, right? Here is the initial growth rate, that is what we call R, and here's the carrying capacity, right? And what kind of equation is this? This is a straight. I'm assuming this is to be straight line. I'm assuming this is to be a straight line, right? So as I said, this is a per capita growth rate. So per capita growth rate is the growth divided by the number of population, correct? You would agree with me that it's going to be the growth, that's the p prime of t, p being the population, divided by the total amount of population, right? We are saying that is equal to this particular the function, the f of p, where if you say p of t is the number of infected people, right? The number of infected people. This is a very simple model, by the way. Number of infected, right? At time t, and we are assuming that the growth rate, or sorry, the per capita growth rate is a straight line. It does not have to be this way. I'll show you in a moment what are the other ones that are more realistic than this. This we are assuming it's always going down. That is not necessarily the case, by the way. There's something called Ali effect. We'll talk about in a moment. And this is the per capita growth rate, right? The growth rate with respect to the population, the growth divided by the ratio between the growth and the population, and we are assuming it to be a straight line. So what is that straight line is going to be? And if you see this straight line, you would agree with me, right? This is an equation of a line. We know how to find the equation of the line. The equation of the line, the easier one is if you know the y-intercept, and if you know the slope, then you can compute it, correct? So here the y-intercept is r, and what is the slope? The slope is the rise over run. Here is your rise, and here is your run, right? So therefore, what is your slope? The slope would be negative r over k, right? So therefore, the equation of this line would be, if you say this is f of p, right? If you say this is f of p, the slope, this is a function of p, right? So that would be, y is equal to, remember, y is equal to mx plus b is what I'm looking at. M is the slope and b is the y-intercept. And m, the slope happens to be minus r over k times p plus r, right? Plus r. In other words, if you're writing it along the y is equal to mx plus b, this would be minus r over k times x plus r, right? So that is the model. So let's take, so therefore the per capita growth rate happens to be this particular equation right there. So let me plug it back in here. If I plug that back in here, ladies and gentlemen, what I'm going to have is the following. What I'm going to have is that P prime of T, the growth of the population divided by P, which is the per capita growth rate, that happens to be minus R over K times P. P is the variable, right? Plus R. And if I simplify this, ladies and gentlemen, the P prime of T equals negative R over K times P. I'm going to multiply the P times P plus R. If I simplify this furthermore, you're going to see this is the same as saying P times R minus R over P. So not R over, that's not a P. That should be a K, R over K, P. And that's your P, the growth rate of that infected, the number of people who get infected, right? The population that, that gets infected. So here is the differential equation model that models the spread of a viral infection, right? Here is a differential equation model that models the spread of the spread of the virus, right? Virus infection, and that assumes, by the way, that assumes in this case is logistic equation, and you can solve them. You can go ahead and solve them. Suppose you see that if you see this, if you treat this as a one constant, and if you treat this as another constant, and you can rewrite this as in general. I'm looking at a generalistic model, right? We can treat this in general as P prime of T equals P times A minus B P. If you want to even make it better, you can say this is Y prime of T equals Y times A minus BY, right? That is a differential equation that we have. And by the way, if you take a look at this differential equation, this is an autonomous differential equation, right? This is an autonomous differential equation. It's a nonlinear differential equation, though. It's an autonomous differential equation. We can solve them using, we can solve this. Excuse. Yes, this is an autonomous differential equation. We know how to solve them. If you know the initial condition, right? If you know the initial condition, we just say the initial condition is y of 0 or y of t naught, it's not necessarily 0 is equal to y sub 0, then this is an initial value problem, and this is going to have a unique solution by the Pickett's theorem, by the way. And we can solve them using a variable separable method. And here is the solution using variable separable method. If you solve them, you're going to have this particular, this is your solution, right? This is going to be your solution, which is P over A minus B P is equal to C1 E A to the T. And even if you simplify this, our goal is to find the P. If you simplify it, again, this is a this is an implicit solution, not an explicit solution. If you try to solve this explicitly for P, then you get this problem right there. You get this A times the C1, that C1 depends on the initial population, divided by B C1 plus E to the negative AT, right? So you can solve them, and here's the solution is going to look like. And if you can graph these, if you can graph them, the graph is going to look like this. So here is the initial amount of spread, the number of people who get infected, and it's going to keep on go forever. It's going to keep on go forever. And this is your K, by the way. That's your carrying capacity. That's your carrying capacity. And then it's going to eventually infect every single one of them, right? That's what that's how the models are going to go. So what I want you to do, is the following. Now that you have a data, right? You know what happened. You know the data last week. You know the data, the number of people infected in the U.S. 2 weeks ago, 3 weeks ago, and so on, so on. So go back to this website. Go back to this website. So here's the data that you can get, right? Let's take a look at the U.S. Wow, it's almost 400,000. So now go back to what happened, the amount of people who got infected. If you take a look at these, right, you can get all these data. If you can get all these data, by the way, if you take a look at them, what happened, the number of people who got infected. Take a look at these. And let me just make it bigger. So take a look at this data. It seems like, well, take a look at for every week. Using this data that we have, you should be able to, fix something as your, look at the data here, right? fix something, let's just say, I don't know. You want to say, let's take a look at from March, right? Let's take a look at from March first week, right? Whatever the data is, March Monday, the first Monday of the March, and the second Sunday of the March, first Monday of the March, second Monday of the March, third Monday of the March, and so on. So now you have a data. Look at the number of people who got infected by this, by looking at this website, right? And then try to model it and using those. So for example, let's just say our T sub 0 is the March. What is the March? What is the first week of March? That is that seems the second, right? Second, the second March, yes, second. All right. So let's see how many people who got infected on the 2nd March. So that's going to be our T sub 0, right? March 2nd. And the T1, let's just say that is March, let's call, we are looking at every week, right? So let's just say that's a 0, that is equal to this, that's a T1, that's a March 9th. And the T2 is equal to March March 16th, and so on, using those numbers, that whatever the amount of population is. I'm just making this up, right? Let's just say it was, let's, rather than making it up, let's actually try to figure out what it is. How many people who got infected March 2nd? March 2nd, the number of people who got infected is what? 118 people, right? And then 149, 217, 262. I don't know if you can see it, right? It's 118, 149, 217. You can kind of, see all the numbers there. So it's 118, right? And then you look at the numbers. Using these numbers, plug it in. Let's just say that's my 0, right? Let's just say that's my 0. Plug in 0, set equal to 118. And then you plug in another, and a couple of more values. Using those values, you can figure out your A, you can figure out your B. Well, actually, we know the A and B, by the way. That's the per capita, that's the carrying capacity, right? K is equal to B over A, by the way. That's a 3 million. In our case, it's a 300 million. Now you can figure out your, now you have, that's our initial population, 118. You can figure out these A's and B's. You can figure out these A's and B's using this data that we have by looking at these numbers. So figure these A and B out. Remember, I think B should be, is it A over B or B over A? It should be B over A, my bad. I think it should be K. The carrying capacity should be B over A, right? In our case, that happens to be 300 million. So you figure out the appropriate B over A, that is 300 million, and using that, try to model the coronavirus and see what is going to happen at the end of March, at the end of April, right? So that is a project. For you. Do that, number one. The second part of, okay, someone is still trying to join in. All right. The second part of the project is the following. I think I'll stop it right here with that. I'm going to modify, well, let's not modify that yet. Let's not do the harvesting there yet. But I want to make it more realistic. Whatever we have is not really realistic, by the way. Usually, there's a person, his name is Ali, not my name, Ali, right? It's called Ali's growth, or Ali effect, right? It's called Ali effect. So what is this Ali effect? So he says, by observing certain populations, there's a nice book in 1930, he says usually the growth, the per capita growth rate of many population, I shouldn't say any population is not, it's not this way. It's not like starting at one point and going to this. It doesn't happen this way. The Ali says, from what he observed usually on the birds and things like that, it usually happens in ecology a lot more, is that it starts somewhere here, and sometimes it could be negative, by the way, right? It starts somewhere here, positive, and then the growth rate, the per capita growth rate increases, and it reaches a peak and then becomes a zero, right? Sometime the Ali says, well, it doesn't happen also that way. This is called, a strong Ali effect. There is something called weak Ali effect, and that says something similar. He says sometimes it starts negative, which means if the population is really, really low, they may not have enough mass to populate. They may not have enough mass to, populate more. So the growth rate is really, really bad. It has to have a critical mass to even for them to grow. Once it reaches the critical mass, and then it's going to grow, the growth rate is going up, and then it reaches the maximum and comes down. Then it reaches the maximum and comes down, right? And I think that may not be the case. These are harder to solve, by the way. These equations are harder to solve, so I'm not going to I'm not going to give you that problem. Let's assume this being our case. Let's assume this being our case, and how do we solve it, right? So what you can do now, again, previously the way that we modeled this one was a line. We kind of modeled it. What kind of shape is this? We say that's a line, we came with a line, right? What kind of shape is that? That looks like a, anybody? That looks like what? Parabola, right? Very good. Now, one of them is going to be a negative number. One of them is going to be a positive number, and that's going to be our carrying capacity, right? That's going to be our carrying capacity, right? Once it reaches everybody, then of course people are going to get recovered. Then it's not going to spread anymore, right? The number of people who get infected is going to go down. So now this equation of the f of p, the growth rate, right? F of p or f of x or f of y, whatever you want to call it, I'm going to say f of p, right? Is going to be some sort of a, since it's a, let's just say, if I suppose if this is a and if this is b, if this point is a and if this point is b, and a is negative and b is positive in this case, it's a quadratic equation. So therefore, this is going to be x minus a times ax minus b, correct? In this case, p minus a times a p minus b. I should say it better. So the f of p is going to be p minus a times p minus b. I know I have minus 1 minutes, right? Minus 1 minute. I understand that. So I have a p minus a times a p minus b. Now, what I want you to do is go back to the data. So therefore, our model, our new model that we have is going to be something like this. P prime of t is going to be p times p minus a. This a is this a is negative. P minus b, the b is positive, right? So let me write it down. A is a negative number that corresponds to this, and b is a positive number that corresponds to this, and the b over a is your carrying, no, in this case that may not necessarily be the carrying capacity. So you can say you may have an appropriate number. I think in this case you can find I think the b would be kind of your carrying capacity, by the way. Yes, the b would be your kind of carrying capacity. Anyway, for sake of simplicity, let's take the b as our carrying capacity. Now I want you to solve this differential equation with the data from the COVID data, and this will be more realistic. This will be more realistic in solving them. So let me show you something. So I'll stop it right here. So that's a project, right? Maybe I'll write it up and I'll send you I'll write it up and then I'll send you a project on your Canvas. You can work on them. Again, this is purely optional. You don't have to do it. If you do it, you should do it so that you look like a nerdy and a geeky. You can kind of model actually what is going on, and also you can predict it pretty decent enough. Decently, you can predict it what's going to happen. If you don't believe me, let me show you something. If you think that this is not a big deal and so on, I don't know if you can see right here. Do you see logarithmic? Do you see this logarithmic there below? Right, logarithmic there. Let me click in it for you. So this is the kind of trying to fit a model there, right? This is the kind of things that are trying to fit a model. So these are using some of the mathematical models and so on. And by the way, here's the daily increase. I think it seems like it's kind of like going up and down. It seems like we may have reached a peak. I hope so. But by looking at this, you can see that it's kind of growing like this. Anyway, I'll stop it right here. Again, this is a project. You don't have to do it. If you do it, you'll get an extra credit. So I want you to model the coronavirus, the amount of infected people in the coronavirus. Again, this is a very simple model, not necessarily very, very realistic model, but it gives you a very good estimate, a basic crude estimate on how do we solve some of these problems. So as an application. All right, I will stop it right here. We'll talk about more applications and solving more differential equations in the next session.